Okay, let's get started. So today I'm going to talk about rectified RF inversion, which is how to do image editing with rectified flows. But before I get to that, I thought we should go through conditional flow matching carefully. So I'll continue from where I left off. Just a note for the next two lectures. Advait is going to present two talks on on what already I'm blanking out. Yeah, thank you. Hardness of posterior sampling, smooth analysis of posterior sampling, and topics around that. So that's Thursday and next Tuesday. So with that, let me get to conditional flow matching, and then we'll come back to, we'll go to RF inversion. So as I said, the references are rectified flows have been really popular recently. So the standard references now with these three were roughly simultaneous. Chang Liu et al. Flowing fast and straight, Lipman et al. Flow matching for generative modeling, and Albergo van den Eyden, which is about stochastic interpolants, which are all essentially flow-based views of generative models. What I'm going to follow in these notes is this tutorial by Lipman et al., Flow Matching Guide and Code, which was from last December. As I said last time, I'll just quickly survey what I did in the last 10 minutes of last class. Okay. A flow model is essentially the following. At time t equal to 0, I get a sample from some distribution. Let's, for concreteness, say it's Gaussian, though it need not be Gaussian. I mean, if you look at Lipman et al.'s tutorial, it's much more general than this. But I'm going to stick to sort of the simplest case so that I can do everything in the next 45 minutes. Okay. And at t equal to 1, you want to get a sample from some data distribution Q star. And what you want to do is to learn a velocity field parameterized by some theta, which transports a sample x0 to x1, meaning you want to find a velocity field such that dx by dt is ut of xt, okay, such that at the terminal, this initial condition is sampled from P0, and the final condition, x1, is some Q star. Okay. So this is like DDIM like setting 2, if you think about it. We took a Gaussian, we transported it across, and the way we found the transportation map is you did the DDPM, write the Fokker-Planck for that to get the density evolution. From the Fokker-Planck's density evolution, you extracted the velocity field because you know that the density evolution and the velocity field are related through the Fokker-Planck or to the continuity equation. You extracted it, and then you got that, you get a flow. Okay, this was one recipe for getting a vector field to transport things. Okay, and so we saw and the continuity equation essentially that connects the density evolution and the velocity field is the following. Okay, it says that if you look at the derivative of the density, okay, that plus the divergence of the probability flux must be 0. It's just conservation of probability mass. If you have a mass flux, the divergence is talking about outgoing mass. The amount of mass that is probability mass that is going out, the probability is conserved over the entire space, and this is essentially a conservation law. That's all it is. Okay, and so this basic equation we have used it again and again in different forms. This basically tells you if you have a PT, you can get a UT out of it in principle by solving this equation, or equivalently, if you get a UT, you should be able to get a PT out of this. So if you want to, therefore, if you want to sort of have a generative model, there are three ways you can think about it. You can say, I want a sample starting from, let's just fix time between 0 and 1. Time evolves from time 0 to 1. At time 0, you find an easy way to say sample something. Okay, so Gaussian noise is 1, but there could be other things as well. And you specify at time 1, I want to get somewhere. And you can specify the sample path, the trajectory you'd like to evolve. That's one way of doing it. A second way of doing this is saying density evolution. I will give you a sequence of probability density functions as a function of time, saying at time 0, I want it to be P naught. At time 1, I want to be Q star. And maybe I'll specify the whole trajectory. This is the trajectory I want. That's another way to specify essentially transport. A third way is through a velocity field. You specify essentially an initial condition and specify a field, a time varying field into which whenever you put something else, it's basically dxt by dt is ut of xt. So you specify ut, again you transport it. Okay. So what we did with all the ddpm, ddim business is use ddpm first, which was a sample part description, to actually derive a density evolution. Once we had the density evolution, use the continuity equation to get a velocity field. We got this velocity field, and then using this velocity field, define DDIM. So what we are going to do in flow is a different analog. We are going to start from a sample path and derive directly a velocity field from that. We will see that essentially, whether you do flow models or whether you do DDPM, DDIM, or as I said, optimal transport, in this setting, they're all essentially the same things. Okay, it's just a different time scaling and parameterization. But you will see under the hood, they're all essentially trying to learn some version of a conditional expectation or a score. Yes.
Do you mean the distribution over
no.
The path, or what's the margin?
I give you no the sample path. I pick an omega and tell you a trajectory. So in a SDE, the sample path is defined by x of t is integral 0 to t x of b of x of s dbs plus something. So it's a trajectory. For each omega, I give you a trajectory. That's all I mean by sample path. It's a random variable. It's a random variable on C0t. If it's continuous, C01 or something like that. Is that that's what I mean by sample path. Okay, so so let me talk about flow matching. So we will start with a sample path. At any time t, I want it to be a linear interpolation between x0 and x1. So x0 is sampled from p0. X1 is sampled from the data distribution Q star. Okay. Now you can ask, how are these two sampled? Okay. I could do independent sampling and then try form a path between these two. I could do some coupled sample. I could say x0 is a low resolution image, x1 is a high resolution image of the same one, and that will give me a coupled sample. Okay. Right? For this, so you could do various types of samples, and you can look at 4 for more details, but I'm going to look at this independent sample here. Okay. So x0, x1 are a product distribution, and xt is just a linear interpolation between those two in this setting. Good. Now,
Some other sampling is that has alpha t and beta t.
yes.
But here alpha t is chosen to be given.
I'm looking at a very special key. You can generalize this way more. You can make it alpha t, beta t, x0, x1 can be coupled. You can, in fact, you can specify what you can do. You could.
What does it make any difference?
Yeah. For the OU process, for example, it can take longer than on one to observe.
Essentially, it's all time scale. This is basic. All these different things lead to different time scaling of the trajectory. So if you look at the SDE for, we did it a few lectures back when we talked about, we took RF and derived the SDE associated with it. Okay, and why would you do it?
Like, does it give any advantage?
You can do it. Okay, there are two ways of thinking about this. One is it's going to give me a different trajectory. Which parts do you want to accelerate? Which parts don't you want to accelerate of the trajectory? Okay, and then how are you going to discretize this after that? Okay, if you use this one, uniform discretization in this one would correspond to a non-uniform discretization of some other one. Okay, so this is an engineering problem, right? At this point.
Yeah.
In terms of theory, okay.
They're all equivalent.
They're all equivalent. That's all I'm trying to say.
Practice, have people noticed that some alpha beta choices are better and others are bad? Or like, why is this even a thing? Why not just use this in beta? Why think of it in 15 different mathematically equivalent ways?
Okay, there are two answers to that. One, I don't think all this, when these various people built these things, there are still people who are saying that they're all different things.
Yeah.
Okay, when actually it's not. I don't think not everybody realizes, at least in this setting, that they're all the same. These things are actually much larger communities. If I change this the joint sample, of course, it's not no longer a diffusion model. Okay, it's something else. If I look at optimal transport with some other cost, it becomes a different thing. But if you specialize it to actually a practical sampling thing, it's my opinion, they all come down to the same thing. Okay, but yeah. I'm not sure everybody will agree with that, but that's what I'm, yeah. Because mathematically it comes back to the same thing. Meaning, if you come up with a different alpha t and beta t here, I can go back there and tell you what's the scaling to be used so that you can get the same thing. So one approach does not, in my opinion, does not give anything more powerful than the others in this specific setting. And so I still have not answered your question about what's the best way to choose alpha t and beta t. But this is all about the times. This is all. But there's a gazillion things about what is the right time scaling to train. Some seem to be better and worse. But whatever you do with one of them, you can do it with the other ones as well. That's all I can say. It's not a clean answer to your question because I'm not telling you which is the best because I don't know. But one approach is not going to give you something more than the other approaches. Okay, but we'll go through the sort of the flow. That's why I took one simplest setting so that you could see all the pieces of this and how it goes together here. So we need, now there's a path and we need to get a velocity field. You need to derive ut for this. So how do you do this? Well, first, let's define the conditional density of xt given the terminal state is x1. Okay, so at time 1, it's I'm going to condition that it's equal to little x1. So then pt given 1. So the notation here is in the subscript here, I'm not putting the random variable, but I'm just putting the times. I'm just following Lippmann's notation. The times corresponding to the random variable. So this is the random variable at time 1, at time t, condition on time 1 of x given x1. That's the notation. And so, well, for a fixed x1, you got a density evolution. And the density evolution is derivative of the density is minus gradient of the conditional velocity field. So this velocity field will always terminate at x1 by definition. The conditional velocity field of x given x1 of the conditional density, right? They have just written again just the continuity equation for this. All right. So now let's write total probability theorem. So therefore, the marginal at time t is the conditional of t given x1 times x1 is from the data distribution, so its density is q star dx. So if I take the derivative, so del by del t, I'll write as little del t. If I take the time derivative of this, I can push the time. I'm just going to interchange the derivative and the integral, so it goes inside. This is the only part that depends on time q star. Now, this is the time derivative of the density, and we know from the continuity equation that it's nothing but the negative of the divergence of the probability flux. So let's just substitute that in. Okay, let's substitute that in. And now you can easily check that the divergence can pop out. Okay, because the divergence is basically nothing but a summation of derivatives. And so you can exchange integral and those derivatives. That's not a problem. I mean, I'm going to assume everything is nice, integrable, all these swaps work out and all that stuff. Okay, so we can pull this out, which says that the time derivative of the density of the unconditional density is nothing but the negative divergence of this. Now let's look at this. Bayes' rule says the posterior, the density of p of one given t is p of t given 1 times the data distribution by pt of x. I've just written Bayes' rule here. So if you look at this, this has a pt, this is the numerator of this. So I can look at this denominator and stick it in instead there. Okay. So which means that we'll get the marginal times p1 given t. So this product becomes p1 given t of x1 given x. Good so far? I'm just checked in Bayes' rule. So if I treat little x1 as a dummy variable, so this has gone away, remember? This whole thing has gone away. It has become this. So x1 is a dummy variable. Let's call it z. Then this is nothing but the expectation of this function with respect to this distribution. Okay. So it's pick a z from this distribution for given x, and this is ut given x. So what we have is the density evolution of pt is minus divergence of PT times this function. But that basically means this must be the velocity field. Okay, so that's all it is. So ut is nothing but the conditional expectation of x given z of of the this is the conditional velocity field. This velocity field, remember, it was defined for if I wanted to terminate at little x1, then what would the velocity field be? We never derived this in closed form. We just said, hey, for this density evolution, this is the conditional velocity field. I never told you what it is. But if you somehow knew that, you're in business. Now, okay, are you good so far? I haven't finished the story yet.
Average out all the paths that I would have gone to, given I'm ending at Z, and just average those.
Exactly. That's all it's saying. Okay.
I want paths to be linear, then I'm
Good. Now we'll use the linearity. Okay. Now, this is the path I want. So dxt by dt is minus x0 plus x1. But dx by dt is also the same as the conditional velocity field. Okay. So I can equate these two and say that the conditional of this given x1 is little x1 minus x0. But what is x0? Well, x0 is xt minus tx1 by 1 minus t. I'm just rewriting this. Okay, so if I substitute that in, then we get that ut, the conditional velocity field given x1, has a closed form solution. That's the key takeaway from all this. Okay, the closed form solution is, hey, wherever I am, go towards x1, and with a particular time scaling, it's accelerating moving. Now going back to Sujay's question, if you change those kappa t's, this acceleration function, the weights would change. Okay, it's how fast you move in different parts of the state space towards the manifold.
You're saying, so I impose this coupling to start with, which was a linear path.
Exactly.
And then you're saying, if this was the joint distribution over data and noise, and I'm at some point, I could just average out all of the linear paths that I was.
So I'm giving you the exactly. I'm giving you the conditional.
Because I started with this.
Of course. I've started. As I said, I need to start from something. In the DDPM setting, we started from the reversal of the OU process, and that gave us our sort of grounding. Here we're starting from something else. And so this gives us a setup, okay? And so if you combine these two, then what you get is that what two? You got this, and you got this, okay? You just combine these two, and what you get is that the velocity field you need to use is simply the conditional expectation of z, which is the, so if at time t I'm in x, estimate pick a sample of what the terminal condition would be, and then take the expected value of this function, which is just z minus x by t. So this essentially gives me this velocity field. This is interesting. If you look at this velocity field is affine in the score again. Look at this. This quantity, the conditional expectation of this says I am at time t I'm in position x. Let's interpret what this is. At time t, we are an x. So given that, just as Jacob said, this quantity is what will the average point I'll end up at time 1 be. Okay. This conditional expectation, we know now from Tweedy's formula, this is nothing but this is affine in the score. Okay, because there's a conditional expectation of what did Tweedy's formula say? Tweedy's formula said the score was equal to conditional expectation plus state. Okay, it's some affine with some weights associated with each one of them. Okay, so that means this creature is also score up to some transfer. There's a minus x, there'll be some weights there. So again, you can see that fundamentally nothing is changing. It is still a score-based system, the flow, with different time scalings, which anyway people would treat as hyperparameters to sort of figure out how to tune these things. Okay. So, okay, that's step. So you could at this point stop and say, done. I'm going to train a model using, score matching, okay, denoising score matching, get a score, get the conditional expectation. I can put it into this, rescale these things, and get a velocity, get a flow model out of it. Okay, so there are two separate blocks in this. One is what are the weights of, right? One is how do you learn a score function or the flow field. The other is what is the dynamic you use with it. You could sort of do any one of these models and go to the other one. Is this good so far?
Because before you showed that the flow matching loss is not the same DSM loss that I plug in.
It's not. I'll get to that in a few minutes. But at this point, I said that if you had this, all these models are giving you some approximation of the score. Okay, I could put it in here and get this velocity field. Now the question is, if you're following this road, then how would you learn the what this is with all so far with the ideal UT? What right, the ideal velocity field. Whereas I actually want to learn something parameters by theta. So let's look at where this road will lead us. So these folks define the flow matching loss. The flow matching loss is the following. Look at the squared error between, so pick a time at random, okay, uniform between 0 and 1. Pick a xt from the density pt. Okay, so given this velocity field, given this true velocity field, there is a density associated with it. How we'll implement it, we'll look at it in a second. Right now, I'm just talking about just a loss function. Given this ut, which is this, there is an associated density pt with it, which is given by the continuity equation. Derivative of pt is minus divergence of pt ut, the probability flux. Okay, so pick an xt, pick a time, and just minimize the squared loss between these two. Okay, there is a flow matching loss. In the paper, actually, is more general. They say that you can, what they write is with respect to any Bregman divergence. You can write it not just with the squared loss, which is a special case of a Bregman divergence, but you can use any F Bregman divergence. Okay, but I'm just sticking to this. Okay, they're just
UP and XT.
because I changed notation halfway through and I screwed up. Thank you. Yeah.
Like one of the papers you mentioned had a simpler geometric picture, which was like I'm at XT. I want to go to X1. This is for training loss, right?
Yes.
So it's like you have made X0, you have XT, X0, X1, and you have XT, like you said. And then you can say that I'm at XT. I want to go to X1. So I should be in the direction X1 minus XT, and the velocity should be in that direction.
I'm going to get to that.
Right? So
I'm going to derive it from this view. You're come to this. Yeah, I want to show that this is equivalent to that. That's the thing. Because I'm in the flow world, you could come from different worlds. So that's the point of the next 10 minutes. Yes, I'm going to, that's all. These are all equivalent is what this next 10 minutes is going to do. Okay, so this is a world of, now I have a flow field and I want to approximate that field. Okay, this seems like a reasonable loss. Okay, the problem with this is to train this, I don't know ut, okay, in a functional form. Okay, I have something as an expectation, but this is not, I can't just say, I want to approximate this ut. I don't really know this as a function. So instead, what you could do is something else, which is what they call the conditional flow matching loss. The conditional flow matching loss is the following. Pick a t uniform 0 to 1. Pick an xt not from the marginal of pt, but first pick a t uniform 0 to 1. Pick a sample from the data distribution, and then conditioned on the data distribution, look at the distribution of xt. So this is the conditional distribution. So xt is now a sample from those paths that lead to that z. Hang on. No, good. hang on, let me finish. But what we are optimizing is the cost function is different now. Okay. Previously, we were trying to match ut of xt to ut theta of xt. Here, we are trying to say, look at a conditional. So look at this slice where z equal to little z1, and then match that, and then average it. So at least at first sight, this looks like a different thing.
Okay. With t theta xt given z, you've just introduced a latent z that would get marginalized, but you haven't.
Yeah. Yeah. Okay. So this is called the conditional flow matching loss. Okay. Because let's stare at these two. Let me shrink it. You can look at these two expressions. Okay. The flow matching loss is with just ut. This is with a conditional ut. Okay. So these two are different loss functions. Why do I care about the conditional flow loss conditional flow matching? Because this has a closed form expression. So this is something I can train with, and we'll see how we do that in a second. Okay? We'll get to that in a second.
Like z minus xt.
Exactly. It is just z minus xt. It is it's xt. Yeah, z minus xt by 1 minus t. Okay, that's all it is. So this is something we can train with. Almost. But we'll simplify this a little bit more in a few minutes.
Wait, is the math the same? It's like you're saying I want to sample xt, but I don't know xt, so I first sample something else, and then sample xt given that.
But then the objective function is different. It's a different function I've put in there. Okay, that's the difference. So the claim is, okay, first of all, there's a squared loss. If you read the article, you will see that all the squared loss can be changed to any Bregman loss. Though in practice, the squared loss is as good as any. And for what is the Bregman divergence? The Bregman divergence is essentially the following. It is if you got a convex function, then it is essentially the linear, if you look at the linear approximation, look at the function value itself, and look at the distance between those two, that's a Bregman divergence. Meaning df of xy is f of x minus f of y minus the grad f x minus y, which is this linear. So it is this. This is the Bregman divergence. Okay. All right. But the only thing we need is the following, that for a Bregman divergence, including the square loss, the following is true. The expected value of the gradient with respect to the second parameter of the divergence is equal to the gradient of the expected value. So of course, these two can exchange. That is linearity. But this goes all the way in. That is what it is actually a two-line proof if you just try to write it yourself. Okay. So the expected value of the gradient of the Bregman divergence is equal to the gradient of the Bregman divergence, the expected value, and y. Always this gradient with respect to the second parameter. Check it yourself. You can just do it. It's a very simple calculation. If to just see this, suppose z had masses only on 2 points. It's some a. It's a z1 plus 1 minus a z2, and just check it through. You'll immediately see this. Follows from the fact that this is linear finally. Okay. All right. So if you have this, then the following statement is true. We are going to prove it, that these loss functions are not the same, but their gradient with respect to theta are the same. Which means optimizing any one of them, the solution is the same as the other one. So this is what is going to give the geometric connection to the other one. And we'll prove this now. So this one, remember, was just xt and time. There were only 2 samples.
Yeah, it must be the same on two.
Yeah, that means there's a constant difference between them.
Okay,
That's all. There are same up to a constant is what we're going to show. Okay. The proof is the following. What is flow matching loss? Pick a t random, pitch an xt from that pt, and look at the squared loss between ut and ut theta. So we want the gradient with respect to theta, the parameters. So that is nothing but the gradient of this, which now goes inside, is the gradient of this quantity. Let's just look at this and just call it y. Then if you use chain rule, then we can write the gradient with respect to theta of this as the gradient with respect to y of this function times the gradient with respect to theta of just this, just chain rule. And now what is UT? This is nothing but the conditional expectation of the conditional flow vector field. Okay, so we will just substitute that in. So we still have gradient with respect to y of some expected value of UT of xt given z, where z is the sample. The rest is left the same. Now there's a Bregman divergence. So it's a gradient of some expectation of some function. There's a y here. This is the same thing as the expected value of the gradient of this function. Okay. Now you'll collapse this chain rule inside. So you have got a gradient with respect to y and a gradient with respect to theta. Collapse. This was the y part of it. Let's collapse it back to basically say that you get the gradient of the conditional field minus ut of xt. Now bring all these expectations together, and there's a gradient still here. Okay. Linearity of expectation, you can pull this out. And this is nothing but the conditional optimization we've had, which is nothing but the gradient of the conditional flow matching. And therefore, you can optimize either one of them. Now, why do you want to optimize the conditional flow matching thing? Simply because now we'll substitute things back in. Look at the conditional flow matching. So you're picking a t, you're picking a terminal, picking from the conditional distribution. But at any time t, we know that x0 and x1 are in fact specifying any 2 points in time will specify the whole trajectory because the straight line trajectory, right? So specifying in this case, we'll just substitute ut is x1 minus xt by 1 minus t. And now what is xt? Xt is nothing, xt can be written in terms of x0 and x1. It's 1 minus t x0. Sorry. So I've just substituted for the conditional field, the closed form expression we had just derived some time back. And equivalently, this gives you the conditional flow matching. So now this is your geometric thing. So we did the geometric thing previously in lecture 15, which is what Sujay sort of referred to. Like you look at these 2 points, you want to do this, you approximate this at any point and average it. And that's exactly what it is. Okay. So you see that these loss functions are the same up to some constant. That's all. Okay. Yes.
The G that you are talking.
G.
I feel like the xt is already dependent on G, right? In the formulation, if you go little above.
More.
Little more now. Yeah. So ut of xt given z.
Yes.
So that z is already the xt is already dependent upon the data, right? So while you are
Correct. Okay. Let's go through this. So I've given a single sample of data point here. Okay, and then it's averaged out. So let's look at what is this though. This has a closed form expression. You agree? So this is the expression for that. So this is what they see here.
Yeah.
Okay, this has a closed form expression here. So we just substitute that in here. I'm just calling that z as x1 now. Okay. Now the key thing here was a sample from t, z, and xt. That is equivalent to picking any other 2 points on the trajectory because a straight line trajectory. Good. So instead, I will write it as between x0 and x1. Okay, that's the trick. I guess that I didn't say explicitly. Because it's a straight line trajectory, I can now equivalently just, all these distributions are consistent with each other, so I can pick any other 2 points which are easier for me to optimize. In terms of expectations, the same thing.
In that case, how it is different from actual flow matching? There also, you
The flow matching was not, okay, there's, the cost function is, the key difference between flow matching and conditional flow matching is the cost. This is the unconditional field I'm optimizing. Here I'm optimizing a conditional field. Okay, and the question is, are these the same when they're averaged? Okay, that's basically what it comes down to. And they're not, but they're up to a constant shift they are, which is why the gradients are exactly the same with respect to theta. Okay, so this essentially says that now we can train this model using this loss, which is much easier to implement, because it just says sample a noise, sample data, sample a random time, squared loss, and now you can just do that SGD. That's it. Okay, you can weight it, you can do all sorts of other things on top of it, but that, yeah. Okay. So this is what I wanted to say about conditional flow matching.
Is it conditional?
Yes.
And then, so what is flow matching?
This is the flow matching loss was LFM, that you matching a flow field U theta. Conditional flow matching is a way to implement flow matching because the gradients of both are the same with respect to theta.
So flow matching as being in progress. But
In velocity field space, flow match. So this is the flow. Okay, yeah. This is the flow matching loss.
okay, and in terms of x1 and x0, what is UV? It has some weird form.
It has some weird form, exactly. That is why we got.
But does that weird formula become simpler if we have xt being just the linear interval?
No,
It's still weird.
it is. So you are asking what is the velocity field associated with it?
Yeah.
It is the score. It is exactly this. Okay, what is ut? It is this one.
Yeah. So how do you make a training? Like, I want to make a training sample, flow matching, but not conditional.
Which is why it's
How do we-
not clear, right? Because you need to sample from PT, which is why you go through conditional flow matching to implement flow matching. Flow matching is the story in the sense of we have a velocity field and we want to implement a velocity, because finally you need a flow. Let's match the flow, but we don't know how to implement it. So we will implement CFM, which gives you the same U star, same theta star as flow matching. If you train that other cost function.
Right.
That is the story here.
Oh, so there is only one loss function. Right? I mean, sorry, there's only one way to make a sample and train on.
Correct.
There's only one. Right?
Yes.
There are many different terminology,
Yes.
but there's only one way to train.
Precisely.
And that's that.
Precisely.
Loss function.
Precisely. For this way of doing things.
Got it.
Correct.
So then thinking of it all this way,
Mhm.
what is the advantage?
For me or
In general, like why do people have many different
I
viewpoints? when,
because
there's
okay.
straightforward the final x1 minus x0, right?
So x1 minus x0 was not a flow matching view. That is exactly a conditional flow matching. So it wasn't clear why that's the right thing to do. Okay, because that is not the flow matching objective finally. So why is conditional flow matching a right thing to do is unclear.
So like maybe a different thing could have been done is that first you have that, and then you show that if you learn exactly from that, then you are evolving product distribution to the right.
That's right. You can because they're all equalities. So you can or you can go about saying, hey, I have this, so I'll give you another thing you could have done. Okay. So this is all in the flow space. But I can say I don't want to go to flow space. I could start with this SDE. Okay. These are different. So if you look at the standard OU process, it's dyt is minus yt dt plus root 2 bt dbt. But this is something else. I could start from this one, do the Anderson reversal, then write the Fokker plan, then train Tweedies using denoising score matching for this one, and you'd get exactly the same thing. This is another way. So there are different ways to actually get to exactly the same thing. But finally, from training point of view, it is the same thing. You take a sample, you noise it to a certain level, and try to predict. Yeah.
So just final clarification for me. So the PF dot given X you are assuming as a linear relationship.
Which can you tell me where to?
In the
Can I go up?
flow matching, we are actually sampling PF dot given X for G.
Yes.
That you are formulating as a linear relationship between
UT and Z. Actually, we proved it. We are not formulating it. We derived that. So this is UT. Okay. Now the question is, what is this function? You're asking what is this function? Okay, good. We are not formulating it as that. Let me see where we have shown this. From 6. Let's go back to 6. So this is what UT is. No, UT given Z. Okay, here it is. Here's the derivation. Dx, so this is your trajectory. D by dt of this is minus x0, x1. But this by definition is ut of xt given x1. Because that is the conditional flow field. Okay. So therefore this is true. And then now you're done. Now you substitute this equation back into that, and you're going to get this to be true. And that's all. So because you have this expression, we know how to now optimize with respect to sample from, because we know how to sample from data from the noise. In the Tweedy's formula, what did we do? We sampled from the data, we added noise to it, which means we sampled yet another noise, you added it, and then you did denoising. Here again, you're sampling two things, a noise and a data, and then you're doing some transformation of that to predict this thing. So essentially the same kind of pipeline it comes down to finally. Okay. It's the weights are all different, but yeah. Is this okay?
Yeah.
In fact, Sujay, for one more this thing. So if you do, it turns out you can do a flow, discrete flow matching for this is all continuous. You can do discrete flow matching. I'll talk about it 2 weeks from now. It has exactly the same story. You can do MDL masked language, masked with the local reversal. You can do flow. You'll get exactly the same thing. The key thing there is to realize that what divergence means in discrete. In continuous, divergence essentially means flux. If I take a small amount of thing, how much stuff is leaving this thing? In a continuous time Markov chain, it is essentially the following. Look at a particular state. Look at the sum of incoming probabilities to that. Look at the sum of the outgoing probabilities minus the sum of incoming probabilities. That is the discrete divergence. If you have that interpretation, every one of these equations looks almost identical, and you will get then your parameterization. Exactly. You'll have a cross entropy, and then if you put in the masking. So this will tell you a very general way of doing things. But then you're going to ask, how do you sample from that? Let me do a mask and all that. You'll see that this will also give you the same thing finally. In terms of the implementation, it comes down to exactly the same thing. So even the discrete world, this analogy is true. And I'll do that like 2 weeks from now. Okay. So once I've done this continuous, it's very fast for me to now set up the whole thing in discrete. Okay, so that brings me to the end of flow matching. The rest of the 20 minutes or so, I'll just go through where I left off with RF inversion. Okay, so so all this was last time. Remember, we did RB modulation and we stopped in the middle and said we want to do inversion with rectified flows. Now we'll talk about how we could do this. Now we have understood that you got a box. So the goal is the following. You got a box, which is a flow model. Okay. And I want to do posterior sampling with it. There are many possible ways of doing it at this point. Now we understand that. Because we have this box which can do flow, well, I can convert it to a stochastic model and do any of the stochastic samplers on top of it. Okay. Various methods we have talked about. or we can try to do directly with the flow model itself. So that's what RF inversion is. It's a direct way to do these kinds of samplings with the flow model itself. And the idea is essentially the following. Let me see. Before I get to the idea, why do you want to directly do it with a flow model? Because if you looked at any of the posterior samplings we did with stochastic things, it involved a gradient with respect to the measurements, either because of the proximal type approach in the RB modulation, or with the earlier things where the gradient needs to be back propagated through and all that. Can you avoid this gray, at least for some kinds of problems, which is text-guided text for problems with text-guided sort of inversions? Can we avoid a backprop altogether? And that's really the motivation for this stuff. Okay, so this is what we saw was any of these flow models do. It takes noise, it moves to the target distribution. Okay, and so what you want to do with an inversion is essentially the following: start from an image, go back to noise, because this is a vector. The fields we saw UT was just an ODE field. So if I just turn the sign around and you have essentially the infinite resolution path, you could always follow it backwards to get back to where you started from. Okay. In practice, you don't have an infinite resolution. You have to discretize things, and things can go bad because there are two problems. You don't have an infinite resolution. You only have a discretized path, okay, at certain points in time. And you don't have both the forward and backward. You only have one direction. So to get to the other one, you go back, you go one way, and then flip the sign and go back the other way. If it's infinitely finely discretized, then you can, doing this operation both ways, you'll trace things forward and backwards. But in practice, you will not, actually. I'll show you some images of, Sundar, you don't look happy.
We're working with ODEs here, like this sign here.
I don't have UT. I have U at this point. I have at this point, at this point, this point, and that.
Yeah.
So if I flip this sign for this one, so I have this one.
Yeah.
If I flip this sign and go back, I will get here, not here.
Okay.
That's what I mean. Yes. Time discretization. That's all I mean. Okay. So what we'd like to do is to start from an image, to do image editing. This is a pipeline we'd like. We'd go back to the noise, then do some text editing, and go forward again. Okay. So flow back and flow forward is what we'd like to build. Okay. Or if you have something which is non-image, but close to an image, we'd like to go again back to get to whatever that space is at time one, then make some edits and move forward.
Would it be impossible? You're saying if I'm here and I look at the gradient of view here and I reverse it, I don't get to the actual point that the gradient there pointed to where I started.
Yeah.
Can I search?
I'll show you what, if you could do various things. I will show you what, I think this image will be useful. So this is, if I start from that, go back and come back, I get back on the image manifold, but I get something that looks very, very different. These are a particular level of discretization. I think this discretization was 20 steps, if I'm not mistaken. But if you discretize much more, then you will not get something far away. Okay, it depends on what level of discretization you're doing.
You're at some time step t+1,
Mhm.
and I'm at some value x.
Mhm.
And you're saying I could go backwards by moving like dx being negative grad ut+1, and that will obviously give me errors.
Yeah.
But could I instead search for a value of xt such that grad?
It's complicated. Search basically means, what does search mean? It's either a gradient, you have to take gradients or something, right? You're doing some local search. You have to do some local gradient descent. It's too expensive. That's what we want to avoid. Yes, you could optimize this, or you could do several points and do some averaging. You could do various things. Any of them are expensive. Okay. Let's see what else we can. We can. Those things are plausible. So what do we do? we do the following. Okay, you got a coupling, but at least as a mental model, you can think of data um, as sort of typical images and sort of close to typical images. And so on the image side, on the noise side, again, you can think of typical Gaussians and sort of close to typical Gaussians, but atypical Gaussians. And presumably, the coupling that you have learned by the conditional flow matching or whatever is going to sort of couple these things to things here and these things to things there. Okay, roughly. So if you invert using rectified flow, or then you basically get to atypical or typical noise. And of course, you have got infinite resolution. You'd get back here. You'd get this back to here. And if you got discretization, you'd get to something. We saw we'll get to some other stuff. What you want to do is to sort of put a second field, a guidance, to bring things back here. Okay, that's what you'd like to do. And so what we'll do is the following. We'll add a second cup. We'll do the following. For every image and for whether it's typical or atypical, okay, during test time, so this stuff is training time. You have learned all this during training time, right? This is your foundation model. During test time, suppose somebody gives you either, say, this image and wants to edit it. Or as another example, somebody gives you this image and wants you to edit it. Okay. So during test time, we'll sample a typical Gaussian and then form a coupling between whatever you start with and the image you want. Okay. For concreteness, let's say this. We found such a coupling. What is the coupling you want? You want to find a path that moves from here to here. So, so you can now specify that initial condition is this, final condition is this. You can put some convex cost for the transportation cost, right? You could put a squared loss. And if you put the squared loss, you can actually solve this problem. Because again, you want something simple, a closed form expression. And for a squared loss, we know what the solution is, given all this stuff we have talked about CFM. It's just a straight line path divided by 1 minus t, some time-scaled version of this path. And if you want to solve this differently, you could use the minimum principle formally. Okay, this is some optimization problem in infinite dimensions, right? And so you want to solve this, you can just write you can use the Pontryagin minimum principle and solve this. But whatever, you can get a closed form expression to go from here to here, and it is just point towards it with the appropriate time scale. That's effectively it. Okay, good. We have this. So now we have got two fields for this image. We have got one which you have just learned to couple from here to here. We've got another which couples to, because of the rectified flow itself, some atypical point. What all we'll do is to sort of interpolate between these two to move the resulting point to be somewhere between these two, so closer to typical, but hopefully capturing enough of the structure of the image itself. Okay, and then once you have that path, invert that path, okay, using these two fields. Okay, there's a controlled and uncontrolled field, and that's all there is to it. Just pick a random, anchor it with that, and then use that pair of anchors to basically, when things are drifting off, to pull things back. That's effectively it. That's all the idea is. Okay, and there's a way of thinking about this from sort of a graphical model perspective. Okay. So right now is the algorithm. So now I'm switching to essentially a story about it, if I want to be blunt. And if you believe that the world is a graphical model, a structural causal model, okay, what is a structural causal model? It's a model of a joint distribution, according to Perlian sort of causal models. I've got n variables, x1 through xn. I've got some joint distribution. And the way I'm claiming that the world joint distribution is going to be generated is there is some exogenous noise, okay, that generates x1, the first exogenous. And x1 and that exogenous noise generates x2. That x1, x2, and that exogenous noise generate x3, and so on. So it's a acyclic directed graph with exogenous noise and basically a acyclic graph connecting x1 through xn. So when you see a sample from this world, the exogenous noise is somebody generates this exogenous noise, and then sends it through this structural causal model to give a sample of x1 through xn. This is sort of the Perlian view of um, of uh, of essentially a world model. So what we have right now in our case is a very powerful world model, which is the flow model. It's been trained on billions and billions of images, and presumably it understands a world of images. Okay. Good. Now, it's also an editable world model. That's the thing which I haven't talked about so far. What do I mean by editable? So going back to the graphical model view of the world, if I want to change cat to silver cat, what the Perlian view of graphical models would say is the following. Hey, I've got a sample. First, do abduction. Abduction essentially is taking your sample and inverting it back to the noise that led to the sample. Okay, so the exogenous noise. So you take that exogenous noise and keep that exogenous noise. Then do editing of the world. So the world is cats are mostly silver. That's my edit. So that means in the graphical model, some edges are going to change potentially. Okay, I'm changing structure of that graphical model, and then flow that same noise, the noise you extracted from the first world, into the second world. This is essentially what is called counterfactuals. Okay, so when they talk about counterfactuals, it means a pair of graphical models with different structure, but both being driven by the same exogenous noise. Okay. So this is this pipeline of abduction, action, prediction is what they call counterfactual reasoning. And what we have done, so what we have talked about can also be interpreted that way, because essentially flowing back goes back to the noise, and then you're doing text conditioning. So these models we talked about are actually text conditional with cross attention through a transformer. It is not just so everything I talked about is just image generation. Really, it's already very well trained as text conditioned generators. So when you change the text, you're changing the structure through the track, whatever your mechanism internally within the model. And then you flow it back is you are resampling the world. And that's all, that's essentially what this whole pipeline has been. Okay. To see examples of this. So an immediate question you should be asking is, oh, first of all, why isn't it that if I take an image, flow it back with no text conditioning and flow it forward, I don't get the same thing? You should if it was had enough no discretization thing. The problem is there is discretization. Okay, so and that basically leads things to move far off. So another way of thinking what we did is we are putting some negative feedback because we are coupling between the actual image sample during test time and forcing to pull back to that. And that essentially corrects for a lot of the discretization noise. Okay. And now you can, so which is what is happening here in this image. You're forcing it to go back to the original image. So I have discretization errors, but I want to correct for that. You can think of it as some perturbation. I want to pull things back. Well, I'm interpolating between two fields. And so it's going to pull it back to that of the cat. Okay, and that's what you can see in this image. With the same level of discretization between this and this, you're getting a much closer image of this. Okay, and now you can start doing text conditioning. Okay, and you can move things around. So, I mean, it's given after all this discussion, now you see that this is actually this is a very straightforward pipeline. It is not, yeah, you can do all sorts of other things, but and the stochastic sampler for this is what we talked about in this. I mean, this if you have a flow model, you can actually get you can get a stochastic sampler for this, and the image quality is quite nice. So let me see if I can show you. Yeah, this is Flux SDE. So all these experiments were with something called Flux, which is a giant flow model. Now, if you want a stochastic model for Flux, now it's clear. We just need to extract the weights and use the flux as not as a flow, but as a score. And then with the right rescaling, and then you can do a stochastic sampler with that. Okay, and you can get really high quality images. Now you ask, why do I even want a stochastic sampler? Flow models are faster, etc. Well, stochastic models, if you are willing to pay the price with smaller step sizes, you can get very high quality images with stochastic samplers. The reason is the flow models have, when you discretize, all the noise comes in the beginning. As time progresses, there's error propagation. A stochastic model is different. is moving towards an invariant measure. So there's a natural attractor back. Even it will wipe out certain types of discretization errors. It's not. But there is there is noise averaging, which is essentially pulling things back, and that essentially helps a lot.
Yeah.
Okay, and so people are using Flux SD for that's one reason. But the other reason is there are a lot of this Flux or any foundation model are essentially large black boxes people have built, and there's a whole bunch of wrappers around it now in literature for doing things. And there are a bunch of wrappers which have been developed for stochastic models. You don't want to rebuild all those tools, okay? So you can just, instead of rebuilding the tools, you can just take this, do a small transformation, and then use that pipeline. And people are doing that as well, okay? In fact, even in sort of large sort of companies, people are actually using Flux SD in exactly that way. So I'll stop at this point. Since it's not a talk, but sort of more of a class, there's other stuff you can say, but I think now you get a picture of flow, diffusion models, and posterior sampling. Next class, we are going to switch back to theory for 2 lectures, and Advait is going to take over. Okay. And then I'll come back and do discrete diffusions till the end of the semester. Thank you.